The mud sucked at Lieutenant Commander John Ouvry's boots with each step as he walked across the Thames estuary mudflat on November 21, 1939, at 11:47 p.m., with the tide having gone out hours earlier, leaving a dark and flat and deadly quiet expanse stretching before him, where cold seeped through his clothing despite layers of wool and oilskin because the temperature hovered just 2 degrees above freezing. 300 yards ahead, and barely visible in the darkness, lay a German magnetic mine that was unexploded and intact and waiting with malevolent patience, having been sitting in that exact spot for 6 hours since the tide had gone out at 5:30 p.m. Half buried in grey Thames mud as a cylinder 4 feet in diameter and 7 feet long, containing 1,500 pounds of high explosive that represented both the greatest threat to British maritime security and potentially the key to defeating that threat if Ouvry could successfully disarm it. He knew the grim statistics by heart because they had been seared into his consciousness through daily briefings at the Admiralty, where charts showed the mounting toll with numbing precision. 79 days of losses that included 56 ships sunk and 128,000 tons of British merchant shipping destroyed and 342 sailors killed by these invisible weapons against which the Royal Navy possessed no defense whatsoever. There was no way to detect the mines sitting on the seafloor, no way to sweep them with conventional minesweeping equipment designed for moored contact mines, no way to stop them from destroying ships that passed overhead, unknowingly activating the sophisticated magnetic sensors that triggered devastating explosions beneath keels where ships were most vulnerable. Until tonight, when everything would change if Ouvry and his team could successfully disarm this mine and take it apart and learn how it worked and find its weakness. Or, alternatively, die trying in an explosion that would vaporize them instantly without leaving bodies to recover. Just a crater in the mudflat and fragments of equipment scattered across half a mile of Thames estuary. Behind him, Chief Petty Officer Baldwin carried the tools in a carefully prepared kit that included wire cutters and screwdrivers and wooden chocks and a stethoscope for listening to the mechanism, with everything selected to avoid any metal that might trigger the magnetic sensor prematurely and cause the detonation they were desperately trying to prevent. They were 300 yards from shore, walking steadily toward the mine that represented simultaneously their greatest danger and their greatest opportunity. Because if the mine detonated during the disarming attempt, the explosion would kill them both while teaching nothing. But if they succeeded in rendering it safe, then British scientists could analyze its mechanisms and develop countermeasures that would save thousands of lives and preserve Britain's maritime lifelines that were essential to national survival. Ouvry reached the mine at 11:53 p.m. and knelt beside it in the cold mud, placing his hand on the metal casing that was cold and wet and covered in barnacles and seaweed from having been in the water for days since being dropped by a German aircraft that had parachuted it into the shipping channel, where it waited for vessels to pass overhead. He felt for vibration that might indicate active mechanisms or ticking timers, detecting nothing because the internal systems were silent and dormant, though that silence provided no guarantee of safety because magnetic mines incorporated multiple firing circuits and anti-handling devices and delayed action fuses that could trigger detonation from any of various disturbances. Ouvry opened his tool bag with deliberate care and extracted the first screwdriver with its wooden handle and brass shaft that had been specifically selected for being non-magnetic, positioning the tip against the first access panel screw and beginning to turn with exquisite caution and awareness that each rotation might be his last if the mine's designers had incorporated anti-tampering mechanisms triggered by vibration or movement. 1/4 rotation followed by stopping to listen for any sound of mechanisms activating, hearing nothing encouraging him to attempt another quarter rotation while stopping again to listen for changes in the mine's internal state that might indicate impending detonation. The access panel was secured by 8 screws that required 14 minutes to remove completely, 14 minutes of absolute concentration, where Ouvry's entire universe contracted to the feel of the screwdriver in his hand, and the resistance of each screw and the sounds or absence of sounds from inside the mine as he worked with the methodical precision of a surgeon performing delicate operations on a patient who might die at any moment from the slightest error. The access panel came free at last, and Ouvry set it aside carefully before shining his flashlight into the interior, where the firing mechanism was revealed as a maze of wires and coils and capacitors and detonators, representing the most sophisticated naval mine ever built by any nation up to that point in history. He began sketching every wire and every connection and every component with meticulous attention to detail, because if this mine exploded and killed him, then someone else would have to make another attempt, and they would need to know what he had found, creating a record that might save future lives even if it couldn't save his own. At 12:47 a.m., he identified what appeared to be the primary detonator through careful tracing of wire paths and examination of component configurations, and at 1:15 a.m., he successfully traced the magnetic sensor circuit that was the heart of the weapon's revolutionary capability to detect ships without requiring physical contact. At 2:03 a.m., he located the anti-handling switch that would have triggered detonation if he had approached the disarming process less carefully, or had disturbed the mine in ways its designers anticipated might occur during salvage attempts. And at 2:31 a.m. he made the critical decision to cut the red wire that would disable the primary circuit and render the mine inert if his analysis was correct, or cause immediate detonation if he had misunderstood the circuit topology. He positioned the wire cutters with hands that were remarkably steady, given the circumstances, and took a deep breath that might be his last before cutting through the insulation and conductor, hearing a soft click that made his heart race until he realized that nothing else was happening, and the mine remained dormant and safe. John Ouvry had just solved the mystery that had been terrorizing the Royal Navy for 79 days, and in the process probably saved thousands of lives that would have been lost if the magnetic mine campaign had continued unopposed. But this story didn't begin on that mudflat in November, but rather 3 months earlier in September, when German aircraft started dropping something new into British waters that was invisible and deadly, and would bring Britain's maritime economy to the edge of collapse. The SS Magdeburg, a British cargo ship displacing 4,800 tons, was entering Swansea Harbour on September 4, 1939, at 2:17 a.m. in what should have been a routine arrival with no warning and no submarine contact and no aircraft sighted, proceeding normally until the ship was 300 yards from the dock when a massive detonation occurred directly beneath the keel. The explosion lifted the ship 2 feet out of the water before her back broke, and both halves folded downward as she sank in less than 3 minutes, killing 23 crew members, while survivors described the same inexplicable phenomenon of no torpedo track and no warning, just a catastrophic explosion from below that seemed to come from nowhere. Naval investigators who arrived at dawn to survey the wreckage immediately recognized that the blast pattern was wrong for a torpedo attack because the damage was too large and too diffuse and centered directly beneath the keel, which was the strongest part of the ship, whereas a torpedo would hit the side and penetrate the hull and explode inside rather than detonating beneath the vessel. This was clearly a mine, but not any type of mine that British naval experts understood, because conventional British naval mines were moored devices, anchored to the bottom, and floating just below the surface, where ships would hit them with their hulls and trigger contact detonators in a system that was simple and reliable, but easy to avoid if you knew the mines were present. This mine had somehow exploded beneath the ship without requiring contact, as if it knew the ship was passing overhead and could sense its presence through some mechanism that naval warfare specialists found deeply troubling because the implications were terrifying for maritime security and naval operations. German scientists had been working on magnetic mines since 1936 in research programs that were conducted in secret and represented years of development and testing and refinement, based on the elegant physical principle that ships are made of steel and steel is magnetic, and as ships pass overhead, they distort Earth's magnetic field in ways that can be measured and used to trigger detonators. The weapon required no contact and no mooring cable and presented no visible threat, consisting simply of a cylinder sitting on the seabed, waiting and sensing and listening for the magnetic signature of ships passing above. And this revolutionary design incorporated several features that made it devastatingly effective against conventional naval defenses. First, it was completely undetectable because it sat on the bottom with no part breaking the surface, making conventional minesweeping techniques that relied on dragging cables or nets completely useless, because you cannot sweep what you cannot see or locate through traditional methods. Second, it was selective in that the magnetic sensor could be calibrated to ignore small ships and trigger only for large vessels including merchants and warships and capital ships, maximizing impact while minimizing waste of expensive weapons on targets that weren't strategically significant. Third, it was devastating in its effects because conventional mines explode against hulls while magnetic mines explode beneath keels, with the gas bubble from the explosion traveling upward and lifting the ship and breaking its back in ways that could split even large vessels, displacing 10,000 tons or more completely in half. Fourth, it created powerful psychological effects because crews never saw the threat coming and had no warning and no time to react, experiencing one moment of sailing in apparently clear water, followed immediately by catastrophic explosions and sinking, creating terror that affected morale and willingness to sail through waters where magnetic mines might be present. By September 1939, Germany had manufactured 347 magnetic mines that the Kriegsmarine designated as LMB, meaning Luftmine B, airdropped weapons that were parachute deployed and ready for combat operations against British maritime targets. The targeting priorities were clearly defined to focus on British harbours and shipping channels and river estuaries, where shipping lanes narrowed and ships had to concentrate, including the Thames estuary and the Humber and the Bristol Channel and the Firth of Forth, all areas where merchant traffic was heavy and naval vessels frequently operated. On September the 3rd, just one day after Britain declared war on Germany, the first magnetic mines were dropped by Luftwaffe aircraft in operations that marked the beginning of a campaign that would quickly escalate to crisis proportions as losses mounted. By September 15th, 12 ships had been sunk representing 15,000 tons of shipping. By October 1st, 27 ships and 43,000 tons. By October 15th, 39 ships and 68,000 tons. And by November the 1st, 50 ships representing 100,000 tons of merchant shipping destroyed, with the rate of losses accelerating in ways that threatened to become unsustainable for Britain's maritime economy. At the Admiralty in London on October 18, 1939, First Sea Lord Admiral Dudley Pound chaired an emergency meeting that included 15 senior officers, along with mine warfare specialists and intelligence officers and scientists from the Admiralty Research Laboratory, all gathered to confront a crisis that was spiraling beyond control as magnetic mines sank ships faster than conventional defenses could respond. The problem was stated with brutal clarity by the mine warfare specialists, who explained that the Royal Navy couldn't detect these mines, couldn't sweep them with existing equipment, couldn't predict where they were located, and couldn't defend against them, creating a situation where British shipping was increasingly reluctant to enter waters that might contain magnetic mines, and ports were beginning to experience disruptions as vessels refused to sail. The economic implications were catastrophic because Britain was an island nation that depended absolutely on maritime trade for survival, importing food and fuel and raw materials and military equipment through shipping lanes that were now contested by an invisible weapon against which there seemed to be no defense. The insurance industry was threatening to declare certain waters uninsurable, which would effectively close those areas to merchant shipping and strangle portions of the British economy. And some merchants were already refusing cargoes destined for ports in areas where magnetic mine attacks had occurred, creating ripple effects throughout the supply chain. The scientists at the meeting explained what they theoretically understood about magnetic mines based on pre-war German research papers and patents that had been published before the weapon became classified. But theoretical understanding provided little practical help because they needed an actual mine to examine and analyze and test if they were going to develop effective countermeasures. The intelligence officers reported that German mine-laying aircraft were being tracked by radar and that efforts were underway to predict where mines were being dropped. But this information didn't help with the fundamental problem of how to neutralize mines that were already in place, or how to protect ships from mines that would inevitably be laid in the future. The breakthrough came on November 21, 1939, when a German mine was recovered intact from the Shoeburyness mudflat after being dropped by aircraft the previous night, and discovered at low tide by observers who recognized its significance. The magnetic sensor inside the mine represented sophisticated engineering that used a horizontal coil to detect changes in the vertical component of Earth's magnetic field, with the system designed so that when ships passed overhead, their steel holes distorted the field, and the coil generated electrical current that charged a capacitor. And when the capacitor reached threshold voltage, it fired the detonator in a sequence that had been perfected through years of development. The engineering was brilliant, and the physics was simple, and the effectiveness was devastating. But Ouvry's careful examination also identified the critical vulnerability that the system required electrical power from batteries, and the magnetic circuit could be interrupted, meaning that if you disabled the sensor, the mine became completely inert and harmless. At 2:31 a.m., he cut the primary circuit, and at 2:58 a.m. the secondary circuit, and at 3:14 a.m. the backup circuit, rendering the mine completely safe and ready for transport to the Admiralty Research Laboratory, where it would be disassembled completely, with every component analyzed, and every circuit traced and every weakness identified. Within 48 hours, British scientists understood the German magnetic mine completely in all its technical sophistication and operational characteristics. And more importantly, they understood exactly how to defeat it through a countermeasure called degaussing that would revolutionize naval mine defense. The principle behind degaussing was elegantly simple in that if magnetic mines detected ships by sensing their magnetic fields, then you could defeat the sensors by eliminating the field and making ships magnetically neutral and essentially invisible to the detection mechanisms. The process involved wrapping electrical cables around ships' hulls and running currents through those cables to generate magnetic fields that cancelled the ship's natural magnetism, producing a net result of zero magnetic signature that magnetic mine sensors couldn't detect. In practice, the implementation was more complicated than the theory, because different ships had different magnetic properties depending on steel composition and hull geometry and other factors, requiring that degaussing currents be individually calibrated for each vessel to achieve effective neutralization of magnetic signatures. But the system worked remarkably well once it was properly implemented, with the first trials being conducted in December 1939 using HMS Border, a minesweeper that was degaussed and then sailed repeatedly over known magnetic minefields without triggering any detonations because the mines simply couldn't detect her presence. By January 1940, degaussing stations had been established in every major British port, with facilities to install cables and calibrate currents and neutralize magnetic signatures for every ship, whether merchant or naval or fishing vessel, that required protection from magnetic mines. By February 1940, the magnetic mine threat had been largely eliminated as a strategic danger because ships could sail through previously lethal areas without incident, and while the mines were still physically present on the sea floor, they had become blind and useless and incapable of detecting targets that no longer triggered their sensors. German mine-laying operations continued throughout this period because the Luftwaffe and Kriegsmarine didn't immediately realize their weapon had been compromised, but the effectiveness dropped dramatically from 18 ships sunk per month in September and October to just 3 ships per month by March 1940, and only 1 ship per month by April, demonstrating that the weapon that had threatened to strangle Britain had been completely defeated through intelligence and engineering and implementation of effective countermeasures. But the story had a second chapter that demonstrated how technological advantages in warfare can reverse rapidly when opponents copy and improve upon captured weapons. Because once the Royal Navy understood magnetic mines, they built their own versions that incorporated everything learned from the German LMB, plus improvements that British engineers developed. The British magnetic mines designated Mark XIV entered production in March 1940, with features including adjustable sensitivity and multiple firing modes and anti-sweeping devices, and delayed activation and remote detonation capability, representing advances beyond the original German design. By June 1940, British submarines and aircraft were laying magnetic mines in German waters, including the Kiel Canal and the Baltic approaches, and the Norwegian coast, and by September 1940, German shipping losses to British magnetic mines exceeded what Germany had inflicted on Britain during the early months of the war, when magnetic mines represented a revolutionary secret weapon. The weapon that Germany had pioneered in secret after years of research became the weapon that strangled German logistics and disrupted their maritime operations, demonstrating the technological irony that characterized much of World War II, where innovations were rapidly copied and improved and turned against their creators. There was a profound irony in how the magnetic mine story unfolded that speaks to fundamental principles of innovation and warfare and strategic planning, because Germany had developed the magnetic mine in secret through 3 years of research and testing and refinement, believing they had created an unbeatable revolutionary weapon that would provide decisive strategic advantage. For 3 months from September to November 1939, they were essentially correct because the weapon was devastatingly effective, and Britain had no defense and no countermeasure, and no understanding of how the mines worked, creating a genuine crisis that threatened British maritime security. But Germany made a critical strategic error by deploying the weapon before they had manufactured sufficient numbers to sustain a campaign that could have been decisive. Because 347 mines in the first deployment sounds substantial, until you realize that number spread across thousands of miles of British coastline represents barely a nuisance rather than an existential threat. If Germany had waited and built 3,000 mines, or 5,000, or 10,000, and then launched a massive coordinated campaign dropping hundreds of mines per night across every major port simultaneously, Britain wouldn't have had time to respond before their shipping lanes closed and their economy collapsed under the weight of losses that couldn't be replaced or mitigated. Instead, Germany deployed early with small numbers and gave Britain time to capture a single mine and study it and solve the technical challenge it represented, and develop countermeasures that completely neutralized the threat within months of the weapon's first use. One mine recovered from a mudflat and disarmed by one brave officer resulted in the entire strategic weapon being rendered obsolete, demonstrating how technological advantages can evaporate when opponents have opportunities to examine and analyze and understand the innovations that initially seemed so formidable. Admiral Karl Dönitz would later write in his memoirs with evident frustration that the magnetic mine represented Germany's greatest missed opportunity of the entire war, a weapon that potentially could have won the conflict in 1939 if deployed properly, but which was thrown away through premature deployment and insufficient production. By the time Germany realized their mistake and attempted to ramp up production and deployment on larger scales, the British had already solved the technical challenge and developed degassing systems that protected their ships and eliminated the weapon's effectiveness, while also copying the technology and producing their own magnetic mines that would be used against German shipping with devastating results. On December 15, 1939, Lieutenant Commander John Ouvry received the Distinguished Service Order in a ceremony at Buckingham Palace where King George VI personally pinned the medal and read a citation that recognized his exceptional bravery and coolness in disarming an enemy mine under circumstances of extreme danger, thereby providing vital intelligence that saved countless lives. When the king asked Ouvry if he had been afraid during the disarming operation, Ouvry thought for a moment before answering honestly that yes, he had been terrified, but the mine had to be disarmed and someone had to do it, and he happened to be there and available for the task. The king then asked what would have happened if the mine had exploded, and Ouvry responded with characteristic understatement that someone else would have tried next, and eventually someone would have succeeded, because the alternative of letting those mines continue killing British sailors was simply unacceptable. The king nodded with understanding and called Ouvry a brave man, but Ouvry demurred and insisted he was simply a man who had done his job under circumstances that required doing that job regardless of personal danger. The magnetic mine crisis of 1939 lasted exactly 79 days from September 4th, when the first mine sank the SS Magdeburg, to November 21st, when Ouvry disarmed the mine on the Shoeburyness mudflat, representing 79 days of terror where ships exploded without warning and harbors considered closing and economic paralysis threatened. But those 79 days also demonstrated something crucial about the technological dimensions of modern warfare, proving that no weapon is truly invincible and no innovation provides permanent advantage, and every advance creates vulnerabilities that opponents can discover and exploit if given sufficient time and opportunity. Germany built what they believed was a revolutionary, unbeatable weapon, but Britain captured one example and analyzed it and understood it and defeated it, then copied the technology and used it more effectively than the original designers had managed, establishing a pattern that would repeat throughout the war. This cycle of innovation, followed by counter-innovation, appeared repeatedly with radar and sonar and proximity fuses and jet engines and guided missiles, where every technological leap triggered counter-leaps, and every secret was eventually discovered, and every mystery was ultimately solved by opponents who refused to accept technological inferiority as permanent. The side that adapted faster and learned faster and innovated faster consistently won the technological battles that occurred throughout the war. And Germany learned this lesson painfully with the magnetic mine, where they created a masterpiece of naval engineering, but watched Britain turn it into obsolete scrap within 3 months. All of this happened because one mine landed in shallow water, where it could be recovered at low tide, and one officer possessed the courage to walk across a mudflat toward 1,500 pounds of high explosive and methodically take that weapon apart wire by wire until he understood how it worked and could render it safe. The mudflats at Shoeburyness, where Ouvry performed his historic disarming operation, are now a protected nature reserve providing habitat for migratory birds in an area that is quiet and peaceful and beautiful, with a small memorial brass plaque that commemorates the events of November 21, 1939, when Lieutenant Commander Ouvry and Chief Petty Officer Baldwin rendered safe the first German magnetic mine recovered intact. The technical development of the German magnetic mine represented years of theoretical work and practical experimentation that began in the mid-1930s when German naval researchers recognized that conventional contact mines suffered from significant limitations in effectiveness and detectability, leading them to explore alternative triggering mechanisms that might prove more reliable and deadly. The breakthrough came when researchers at the Torpedo Research Institute realized that ships' steel hulls created measurable distortions in Earth's magnetic field that could be detected by sensitive instruments, and that these distortions followed predictable patterns based on ship size and composition and speed, making it theoretically possible to design sensors that would trigger only when appropriate targets passed overhead. The early prototypes tested between 1936 and 1938 used simple magnetic coils wound around ferrous cores, but these early sensors proved unreliable because they couldn't distinguish between ships and other magnetic disturbances, including geological formations and sunken wrecks, and even magnetic storms that occasionally affected Earth's field in ways that caused false triggering. The refinement process required developing more sophisticated coil designs and electronic filtering circuits that could discriminate between target signatures and environmental noise, gradually improving reliability until prototype mines achieved acceptable performance in controlled tests conducted in the Baltic, where they successfully detected and tracked test vessels while ignoring non-target disturbances. The production version, designated LMB, incorporated a horizontal detection coil positioned to sense changes in the vertical component of the magnetic field, which proved more reliable than attempts to sense horizontal components that were affected by the mine's orientation on the seafloor. The coil was connected to a capacitor through a circuit that accumulated charge when magnetic disturbances of appropriate characteristics occurred, and when the accumulated charge reached a threshold voltage, it closed a relay that fired the detonator in a sequence that was designed to explode the mine at the optimal moment, when the target was directly overhead and most vulnerable to the upward-directed blast. The explosive charge consisted of 1,500 pounds of hexanite high explosive, chosen for its stability in water and its resistance to premature detonation from shock or temperature changes, arranged in a configuration that maximized the gas bubble effect when detonated beneath ship keels. The mine casing was constructed from non-magnetic aluminum alloy to prevent the mine itself from creating magnetic signatures that might interfere with the sensor's ability to detect passing ships, and the entire assembly was designed to be as hydrodynamically stable as possible, so that mines would sink to the bottom in predictable orientations, rather than tumbling or drifting with currents. The deployment method involved dropping mines from aircraft using parachutes that slowed the descent and ensured mines entered the water at controlled velocities that prevented damage to sensitive internal mechanisms, with the parachute designed to separate from the mine after water entry, so it wouldn't interfere with the mines settling to the bottom. The Luftwaffe developed specialized tactics for mine-laying operations that involved approaching target areas at night or in poor visibility to avoid detection, flying at altitudes between 500 and 1,000 feet to ensure parachutes had time to deploy properly, and spacing drops at intervals calculated to create effective minefields that covered shipping lanes without wasting mines in areas where ships rarely passed. The targeting priorities for German mine-laying operations reflected careful analysis of British maritime traffic patterns and port configurations, with particular emphasis on choke points where shipping had to concentrate, including harbour entrances and river mouths and navigational channels where ships couldn't maneuver around suspected mine areas. The Thames estuary received particular attention because it served as the primary approach to London and handled enormous volumes of commercial traffic, along with naval movements to and from major bases, making it an ideal location for creating maximum disruption with minimum expenditure of mines. The SS City of Paris, a passenger liner that had been converted to cargo service, struck a magnetic mine in the Thames estuary on 11th, 1939, and sank in 17 minutes with the loss of 43 crew members and passengers, demonstrating the weapon's ability to sink even large vessels with single hits. The explosion broke the ship's back amidships and caused catastrophic flooding that overwhelmed damage control efforts, and survivors described hearing no warning and seeing no indication that danger was present until the massive detonation lifted the ship and broke her structure beyond any possibility of salvage. HMS Gypsy, a destroyer operating in the Thames estuary on November 21, 1939, struck a magnetic mine just hours before Ouvry began his disarming operation on the recovered mine at Shoeburyness, and the destroyer sank so quickly that 106 crew members were killed, while only 29 survived to be pulled from the water by other vessels. The loss of a modern destroyer to a weapon that cost a fraction of the ship's construction price demonstrated the economic efficiency of mine warfare from Germany's perspective, though this efficiency advantage would evaporate once Britain developed degaussing countermeasures that rendered the mines largely ineffective. The production facilities for German magnetic mines were located primarily at the torpedo arsenal in Eckernförde, where workers assembled mines from components manufactured at various locations throughout Germany, with electronic components coming from firms like Siemens and explosives from chemical works in the Ruhr and casings fabricated at metalworks near Hamburg. The production rate in late 1939 averaged approximately 20 mines per day, insufficient to sustain the campaign at the intensity required to achieve strategic effects. And this production bottleneck resulted from the complexity of the electronic components and the need for careful quality control to ensure mines functioned reliably after being dropped from aircraft and immersed in salt water for extended periods. The German Naval High Command requested production increases to 500 mines per month in October 1939, after the weapon's effectiveness became apparent. But German industrial capacity was already fully committed to producing submarines and torpedoes and ammunition for the army, making it difficult to allocate additional resources to mine production without reducing output in other critical areas. This resource allocation dilemma reflected broader problems with German war planning, where multiple programs competed for limited industrial capacity and raw materials, forcing difficult choices about priorities that often resulted in no program receiving sufficient resources to achieve decisive results. The British countermeasure development progressed rapidly once the recovered mine provided detailed information about sensor characteristics and triggering mechanisms, with research teams at the Admiralty working around the clock to design and test degaussing systems that would protect ships from magnetic detection. The first experimental degaussing installation on HMS Border involved wrapping a single loop of heavy electrical cable around the ship's hull and connecting it to a generator that provided direct current calculated to cancel the ship's magnetic signature. And tests conducted by sailing the ship over known magnetic minefields confirmed that the system worked as predicted by preventing mine detonations. The challenge in scaling up degaussing from experimental installations to fleet-wide deployment involved developing standardized procedures that could be applied to the enormous variety of ship types and sizes in the British merchant and naval fleet, each with different magnetic characteristics requiring individual calibration. The solution involved establishing degaussing ranges, where ships could be sailed over sensitive magnetometers that measured their magnetic signatures from multiple angles, allowing technicians to calculate the precise current required to neutralize each vessel's field and providing verification that the degaussing system was functioning correctly after installation. The economic impact of the magnetic mine campaign on British shipping was substantial, even during the relatively brief period before degaussing became widespread, because insurance rates for voyages in mine-affected areas increased dramatically, and some ship owners refused cargoes altogether rather than risk their vessels in waters where invisible mines might be present. The Port of London experienced significant disruptions during October and November 1939, as incoming vessels delayed entry until tides were favorable for avoiding suspected mine locations, creating congestion and delays that rippled through the entire supply chain and affected industrial production that depended on imported raw materials. The psychological impact on merchant sailors who had to sail through waters where magnetic mines might be present created recruitment and retention problems for shipping companies, because even men who were willing to face U-boat attacks and surface raiders balked at the prospect of being sunk by invisible weapons that gave no warning and provided no opportunity to fight back or take evasive action. The knowledge that magnetic mines killed indiscriminately regardless of lookout vigilance or ship handling skill created a sense of helplessness that affected morale more severely than conventional threats where crew skill and alertness might make a difference in survival. The German mine-laying aircraft used for deploying magnetic mines were primarily Heinkel He-111 bombers that had been modified to carry the heavy mine loads, with bomb bays adapted to accommodate the cylindrical mine casings and release mechanisms designed to deploy parachutes at the correct moment during the drop sequence. These aircraft flew missions at night when detection by British fighters and anti-aircraft defenses was less likely, navigating to target areas using radio beacons and dead reckoning, and occasionally visual landmarks when weather permitted, with crews trained to recognize specific harbor entrances and river mouths that served as aiming points for mine deployment. The British countermeasures against German mine-laying aircraft included radar-equipped night fighters and anti-aircraft batteries positioned around likely target areas, though these defenses achieved limited success because the mine-laying aircraft approached at low altitudes where radar detection was difficult and anti-aircraft fire was less effective. The most successful countermeasure involved intelligence warnings based on German radio traffic that sometimes revealed when mine-laying operations were planned, allowing ships to avoid affected areas during periods when mines were being dropped and immediately afterward, before British minesweepers could attempt to clear the newly laid weapons. The development of minesweeping techniques for magnetic mines represented a significant technical challenge because conventional sweeping methods that dragged cables or nets through the water couldn't affect mines sitting on the sea floor, requiring entirely new approaches based on triggering the magnetic sensors deliberately from safe distances. The solution involved deploying large electrical coils towed behind minesweepers that generated powerful magnetic fields simulating ship signatures, causing mines to detonate when the coil passed overhead and clearing paths through minefields that could then be marked with buoys for safe navigation. The LL sweep, as this magnetic minesweeping system was designated, represented a brilliant application of the same physics that made magnetic mines effective, using the mine's own sensor characteristics against them by creating artificial magnetic signatures that triggered detonations without requiring physical contact. The system required substantial electrical power to generate sufficiently strong magnetic fields, necessitating installation of large generators on minesweeping vessels and heavy electrical cables capable of carrying the high currents involved. But once perfected, the LL sweep proved highly effective at clearing magnetic mines from shipping lanes and harbor approaches. The long-term impact of the magnetic mine campaign on naval mine warfare doctrine was profound and lasting because the weapon demonstrated that sophisticated triggering mechanisms could make mines far more effective than simple contact devices, leading all major navies to pursue similar technologies and develop increasingly complex mine designs throughout the remainder of World War II and into the Cold War period. Modern naval mines incorporate acoustic sensors and pressure sensors and magnetic sensors in combination, creating multi-influence weapons that can distinguish specific ship types and avoid triggering on mine countermeasure vessels, representing the continuing evolution of concepts that began with Germany's magnetic mines in 1939. The story of Lieutenant Commander Ouvry's courage in disarming the first recovered magnetic mine became legendary within the Royal Navy and inspired other bomb disposal personnel who faced similar dangers throughout the war, demonstrating that individual bravery and technical competence could overcome even the most sophisticated weapons when circumstances permitted examination and analysis. Ouvry continued serving in mine disposal and explosive ordnance disposal roles throughout the war and survived to retirement, though he rarely spoke publicly about the Shoeburyness operation and consistently deflected praise by insisting he had simply done his duty under circumstances that required action regardless of personal risk. Chief Petty Officer Baldwin, who accompanied Ouvry on that dangerous walk across the mudflat, also received recognition for his courage, being awarded the Distinguished Service Medal for his role in the operation. And he continued serving in the Navy's mine disposal branch, where his experience with the German magnetic mine made him valuable for training other personnel who would face similar challenges. The partnership between officer and enlisted man working together to overcome a deadly threat exemplified the Royal Navy's tradition of cooperation across ranks when facing common dangers that made distinctions of status irrelevant. The memorial ceremonies held annually on November 21st at Shoeburyness served not only to honor Ouvry and Baldwin, but also to remember all the sailors and civilians who died in magnetic mine attacks during those 79 days before effective countermeasures were developed. Recognizing that the weapon's defeat came too late for the 342 men who had already been killed by mines that exploded beneath their ships without warning. Every year on November 21st, veterans and naval officers and historians gather to lay wreaths and remember that cold, dark, dangerous mudflat where Britain won the first technological battle of World War II, not through superior weapons or larger fleets or better tactics, but through courage and intelligence and one man's willingness to walk 300 yards across mud towards certain death if his analysis proved wrong, and cut the right wire that rendered the mine safe and provided the intelligence that would save thousands of lives.